All right, so chapter 7, we're going to be switching gears and we're going to be talking about properties of trigonometric functions. So our motivating question to get us started is, well, what is an identity? So the formal definition of an identity is the following. So an identity is an equation that is true for every input in its domain. So let's think about that for a second. So an identity is an equation that is true for every input in its domain. So let's take a look at our first example. From our sheet here. So we've got the equation 3 times x minus 1 plus 5 is equal to 3x plus 2. Well, let's see if we can guess a solution to this equation. So if I just guess x equals 2, I could plug that in and see if it's true. So that's 3 times 2 minus 1 plus 5. And I want to know, question mark, does that equal 3 times 2 plus 2? Well, 2 minus 1 is 1, 3 times 1 is 3, and 3 plus 5 is 8. And I want to know, does 8 equal, well, 3 times 2 is 6, and 6 plus 2 is 8. So it seems that I was able to successfully guess a solution. All right, well, let's try another one. What if I just guess randomly x is equal to 6? Well, that's 3 times 6 minus 1 plus 5. And I want to know, is that the same as 3 times 6 plus 2? Well, 6 minus 1 is 5. 3 times 5 is 15 plus 5. And 3 times 6 is 18. So that gives us 18 plus 2. And 15 plus 5 is 20, and 18 plus 2 is 20. So that also worked. It turns out that if I just keep randomly guessing, in fact, for every x that I guess, this will always work. And the reason for that is that this is an identity. We're going to refer to it as a trivial identity. Because if we were to distribute into our parentheses here, we would see that this would give us 3x minus 3 plus 5, and then the right-hand side was 3x plus 2. And if I collect my like terms, negative 3 plus 5 gives me positive 2. I get 3x plus 2 is equal to 3x plus 2. So it becomes really apparent at this point that no matter what x value I pick, the left-hand side will be the same as the right-hand side. The reason we call this a trivial identity is because they are algebraically equivalent. So if I just distributed that 3 in and collected my like terms, aka simplified, I get that both sides of the equation are exactly the same. Well, our goal in this chapter is we are going to be studying trigonometric identities, and they're non-trivial. And what I mean by that is we're going to find things that fit this definition. So remember, an identity is an equation that is true for every input in its domain. So we're going to have two different trigonometric expressions that look very, very different, but it turns out that they are going to be exactly the same. So let's take a look at our next example. So example number 2. If I take a look at this, I have y equals the sine of 2x, and then I have y equals sine x, or 1/2 the sine of 2x, and y equals sine x cosine x. If I were to look at each of these, they do not appear to be the same. But let's do a little bit further of an analysis. So let's go ahead and press our y equals, and let's graph the left-hand side. So let's call this guy y1. So I have 1/2 the sine of 2x. Well, let's go ahead and graph that. While my calculator's thinking, I'm going to mark that I put this in as y1. And let's zoom in a little bit. So I'm going to hit my window. I'm going to leave my x max and x min how they are, but let's change my y max and my y min to 1, or -1 and 1. And change my y scale to 0.1. So now when I graph, I do see my sine function, and it bounces up and down as we would expect with a period of pi. So then let's go ahead and graph this second equation as y2. So I go y equals, and I'm going to graph sine x cosine x. So I press graph again, and when I do so, I can't tell the two graphs apart. In fact, it looks like there is only one graph present. So let's keep investigating. So let's compare our table of values. So if I go second table, and I look at the table of values that's generated by y1 and y2, we get the following, where they have all of the same output values. So this suggests that they are the same. One half sine 2x is the same as sine x cosine x. So, in other words, in terms of an equation, we would have 1/2 the sine of 2x is the same as sine x cosine x. So we haven't proved that these two things are the same yet, but based on that evidence, it is suggested, and it's reasonable for us to believe, that this is true for every x. And if that's the case, that would make this an identity. So we'll show that this actually is an identity a little bit later, but for right now, we're just going to leave it as it is and believe for a minute and a little bit later on we'll come back and show that this is actually an identity. So our goal then is we need to build up a whole bunch of identities. So before we do that, let's go back to what an identity is. So an identity is an equation that is true for every input in its domain. So that means that 1/2 the sine of 2x is the same as the sine of x times the cosine x. So one of the things we're going to be able to do then with identities is if I ever see sine 2x, I could, or 1/2 sine 2x, I could replace it with what it's equal to. Because one of our fundamental properties of algebra is that we can always replace things that are equal with things that they are equal to. All right, so we actually do know some identities already. We didn't call them identities, but in chapter 6, we had the following identities. So the first group that we came across in chapter 6 were the reciprocal identities. So we had that 1 over sine theta is the same as the cosecant of theta. We have 1 over the cosine of theta is equal to the secant of theta. And we had 1 over tangent theta is the same as the cotangent of theta. We had our other reciprocal identities, which is 1 over cosecant theta then pairs with sine theta. 1 over secant theta is the same as cosine theta. And 1 over the cotangent of theta is the same as tan theta. So we have these identities. So if we ever see, for instance, a 1 over the cosecant of theta, we can just rewrite that as sine theta. The other non-trivial identities that we had involved even and odd functions. So we had that the sine of negative theta was the same as the negative sine theta. And we had that the cosine of negative theta was the same as cosine theta. And we had that the tangent of negative theta is the negative tangent of theta. So these were some of our identities from chapter 6. All right, so now our goal is to develop some identities. So the first thing we want to talk about are called the Pythagorean identities. So as their name suggests, they are going to be related to the Pythagorean theorem. So if we look at our unit circle, and remember our unit circle has the equation x squared plus y squared is equal to 1. Well, by definition on the unit circle, what was x equal to again? So by definition, x was the cosine of theta. And on the unit circle, we had y. And y by definition is y equals sine theta. Well, if I put x and y, if I substitute x and y into the equation of the unit circle, we would get cosine theta squared plus sine theta squared is equal to 1. And this is what is referred to as the first Pythagorean identity. The reason we call it the Pythagorean identity is if we look at this triangle that we have right here, the Pythagorean theorem is a squared plus b squared equals c squared, but we're on a unit circle, so we know its radius is 1, and if we were to call our x coordinate this side of the triangle A, and if we call this side of the triangle B, we would then have a squared plus b squared equals 1 squared, which is exactly the equation that we had here. So that's the reason that we call these the Pythagorean identity. We're going to come back to that, but before we expand, we do need to talk about some notation and conventions that we are going to use with trigonometric functions. So let's go on a sidebar for just a second. So for exponents on trigonometric functions, we will write cosine, and then we're going to put the exponent in between the function name and the argument. So we will write cosine squared theta instead of cosine theta parenthetically squared. So we have a warning here, and that is that sine squared of theta does not equal sine of theta squared. So let's talk about what each of these symbols mean. So sine squared theta, where we put the exponent in between the trigonometric function and the argument, this tells us to find or to calculate sine theta, then square the result. So in symbols, sine squared theta is sine theta times sine theta. The other one, if we have sine theta squared, this tells us to square theta, then find the sine of the result, or calculate the sine of the result. So in symbols, this one means the sine of theta times theta. So we are going to get two different values depending on how we do this. To make things even weirder, our calculator doesn't use the notation that everything else is going to use, which is the first one. So for instance, if I wanted to find the sine of pi over 3, I would get this value. Oh, let's do the sine of pi over 6, my bad. Which is a half. So if I want to find the sine of pi over 6 squared, I would go sine pi divided by 6 and square it. So notice I can't put the exponent in between the sine and the pi over 6, even though that's how it's going to appear in my labs or in any math book. If I wanted to square the inside, I have to add an extra set of parentheses. So pi divided by 6 squared, then parentheses. And that would give me the sine of pi over 6 squared, which is the sine of theta times theta. So the sine of pi divided by 6 times pi divided by 6. And we'll get that same value. So we have to be just a little bit careful as we're putting these things in to our calculators and reading this. All right, so now putting all of this together, so using this notation, gives the following identity, which is sine squared theta plus cosine squared theta is equal to 1. And this is referred to as the first Pythagorean identity. So if we go to our handout for our unit circle, we will notice that on on our unit circle, on the one side, we did have our unit circle that we've been using. On the other side, we have a list of trigonometric identities. So the unit circle handout isn't going to have every possible trigonometric identity, but it does have some ones that are important and that we're going to use. So this has a list of quite a few of our trigonometric identities. We will be going over these. And then in the bottom right-hand corner, there are a couple of things that aren't trig identities that we will talk about, namely the law of sines and the law of cosines. And we'll get to those a little bit later. So on our handout, we have the following. Three identities. So sine squared plus cosine squared equals 1 is called the first Pythagorean identity, and there are a couple of other Pythagorean identities. So let's go ahead and talk about some of the properties of each of these. So the first thing we need to remember when dealing with identities is an identity is an equation that is true for every input in its domain. So since these identities are equations that are true, that means I can use the properties of equations on these identities. So we can use algebra to write these in equivalent forms. So one of the fundamental rules of equations says I can add or subtract the same thing to both sides. So for the first Pythagorean identity, if I subtract cosine squared from both sides, it gives me the new equation, sine squared theta is equal to 1 minus cosine squared theta. Similarly, if I subtract sine squared from both sides, it tells me that cosine squared of theta is equal to 1 minus sine squared theta. So we've rewritten the first Pythagorean theorem in two equivalent forms. So sine squared plus cosine squared equals 1 is actually three identities in one. The first one is that sine squared plus cosine squared is the same as 1. The second equivalent form is that sine squared theta is the same as 1 minus cosine squared theta. And the third equivalent form is cosine squared theta is equal to 1 minus sine squared theta. So we can manipulate trigonometric identities using the properties of equations to get more trigonometric identities. All right, so we've talked about where the first Pythagorean theorem came from. So the question then is, well, where did 1 plus cotangent squared theta equals cosecant squared theta come from? And similarly, where did 1 plus tangent squared x equals secant squared x come from? To obtain these two identities, so to obtain the other two Pythagorean identities, we divide the first Pythagorean identity by sine squared x and cosine squared x. So if I start with the first Pythagorean identity, sine squared x plus cosine squared x is equal to 1, if I divide everything by sine squared x, well, let's do cosine squared x. So by definition, sine over cosine is tangent. So we get tangent squared x. Anything divided by itself is 1. And the reciprocal identity for cosine, so by definition, 1 over cosine is secant. So we would get then tangent squared x plus 1 is equal to secant squared. Oh, well that is algebraically equivalent to this Pythagorean identity. All right, so let's go ahead and work a couple of examples. So example number 3, we wish to simplify this expression. So we have sine x times cotangent x minus cosecant x. So let's go ahead and distribute the sine x into our parentheses. So when I do so, I get the following. So to help keep me organized, I'm going to mention the properties that I'm using during each step of my simplification. And then what I'm going to get. So the first thing I'm going to do is distribute. So I distribute my sign in, and that gives me sine x times cotangent x minus sine x times cosecant x. So that's my first step in simplification. And then I'm going to use the definition of cotangent and the definition of cotangent is that the cotangent is the same as cosine divided by sine. And the second thing I'm going to use is the definition of the cosecant of x. And the cosecant of x is 1 over sine for our identity. So we have sine x times cotangent, and cotangent is cosine over sine, minus our sine just comes down. So we use these two things, and now we're just going to reduce. So the sine and the sine reduce out, and the sine and the sine reduce out, and finally we're left with that this is the same as cosine x minus 1. So after we distributed and used some of our definitions or trigonometric identities, we were able to simplify the expression sine x times cotangent x minus cosecant x into the cosine of x minus 1. So this 2-column example that I just did is something I'm going to do throughout this chapter, especially when we get to formal identities a little bit later, where on one side I'm going to write down what it is that I'm doing, and then on the right-hand side I actually execute whatever it was I said I was going to do. And this helps keep us organized and also helps keep our identities true. All right, let's take a look at our next example. So example 4. Wants us to do the same thing. We want to simplify cosine squared x times sine squared x plus sine to the 4th of x. So the first thing I'm going to do is factor out the GCF. So my greatest common factor in this case is I have a sine squared here and a sine to the 4th here. So my GCF is going to be sine squared x. And if I factor out a sine squared x, I'm then left with cosine squared x plus sine squared x. The next thing I'm going to use is the Pythagorean identity. And the Pythagorean identity, remember, is cosine squared x plus sine squared x is equal to 1. So then my sine just comes straight down, so I have sine squared x. But cosine squared x plus sine squared x, well, this is just going to be the same as 1, which is then equal to sine squared x. So cosine squared x times sine squared x plus sine to the fourth x reduces to, or simplifies down to, just sine squared of x. Alright, so one more example before you guys get a U-try to work on. So we wish to simplify the following. So based on what we did in the previous two problems, we're going to need to do some algebra most likely. And let's go ahead and get started. So let's focus on this piece right here for a moment. And we're going to talk about a strategy. So overall, when we look at this rational trigonometric function, we notice it has a sine squared plus sine t minus 3, and then a 1 minus cosine squared t minus sine t. This equation has almost, or this expression has almost exclusively sine functions. In fact, the only place it doesn't have a sine is with those cosines. So one common strategy is to try to write everything in terms of sines. So we can use the first Pythagorean identity to help us simplify this. And if we go back to when we were talking about our first Pythagorean identity, notice the first Pythagorean identity had some equivalent forms. The base form is sine squared plus cosine squared equals 1. Well, we don't have that, but we do have something that looks like this. We have 1 minus cosine squared theta. And what is 1 minus cosine squared theta the same as? Sine squared theta. So we're going to use this in the form that 1 minus cosine squared theta, or in this case t, is equal to sine squared t. In doing so, we then have 2 sine squared t plus sine t minus 3 all over sine squared t minus sine t. All right, so our first Pythagorean identity helped us out here. The next thing we need to do is factor. And we have an example in the numerator of what is called a trigonometric polynomial. A trigonometric polynomial So a trigonometric polynomial is a polynomial composed with a trigonometric function. So what I mean by that is that we need to factor this trigonometric polynomial. Well, this is a trigonometric polynomial with 2x squared plus x minus 3, where x is equal to sine t. Because if I were to replace all of the x's in 2x squared plus x minus 3 by composition with this, I would get 2 sine squared t plus sine t minus 3. So we need to factor this polynomial. So we can factor 2x squared plus x minus 3. We have 2x and we have x, and we're going to have plus 3 minus 1 for our factorization. So then, if I were to factor that, where x is this, then this really factors into 2 sine t plus 3 times sine t minus 1. So we factored our trigonometric polynomial to get 2 sine t plus 3 divided by sine t, take away 1, all over sine squared t minus sine t. Well, we now need to factor the GCF out of the denominator. So our GCF in the denominator is just going to be sine t. And then that leaves behind a sine t minus 1. And then in our numerator, we still have 2 sine t plus 3 times sine t minus 1. So finally, after all that factoring, we're left to our very last step, which is to reduce. So then the sine t minus 1 and the sine t minus 1 reduce out, and we're left with just 2 sine t plus 3 all over sine t. So a couple of key things we want to go back to, which is factoring trigonometric polynomials. If it helps, you can rewrite them as the decomposition and factor the polynomial in the way that we always have, and then resubstitute in, which is what I did in blue over here. And sometimes for people that's a little bit easier to visualize. All right, so to resolve our U-try, the first thing we're going to do is distribute. So if we distribute everything out, we're going to get 1 times 1 is 1. 1 times sine is sine theta. And then we distribute in our sine theta and our negative sine theta. So we get negative sine theta times positive 1 is negative sine theta. Negative sine theta times positive sine theta is negative sine squared theta. And then we're going to reduce. So a positive sine theta and a negative sine theta reduce out. And then that leaves us with that over cosine theta. So finally, we get 1 minus sine squared theta over cosine theta. And then we're going to use the first Pythagorean identity, which is 1 minus sine squared theta equals cosine squared theta. So then we get cosine squared theta over cosine theta, and we reduce once again, leaving us with just cosine theta. So that would be our solution. All right. So let's jump to our next example. So example 6, we want to express as a trigonometric function with no radicals. So this is a technique for simplifying and reducing certain types of algebraic expressions involving radicals. So to simplify this expression, we're going to use the substitution x equals 3 tangent theta. So in the homeworks or in any problem I would give you on a quiz or a test, we will supply the substitution. You just need to know how to simplify the expression. So the first step is, given this substitution, we're going to substitute it into our equation. So that's going to give us 9 plus, and we replace x with what it's going to be the same as, which is 3 tangent theta. And then 3 tangent theta squared is going to be 9 plus 3 times 3 is 9, and tangent times tangent is tangent squared theta. We now have a common factor of 9, so we're going to factor out our GCF, and our GCF this time is 9. And from the first Pythagorean identity, we have that 1 plus tangent squared theta is equal to secant squared theta. So now that leaves us with the square root of 9 times secant squared theta. Well, 9 is a perfect square and secant squared is a perfect square, so the square root of 9 is 3, and the square root of secant squared is just secant. So after making that substitution and simplifying, we get that that reduces to 3 secant theta. Interesting, interesting. All right. So it's now your turn. Let's have you guys go ahead and work your U try. All right, and so for this one, the substitution that we're going to need to make is x is equal to 2 sine theta. So, all right, so once again, to resolve this, we're going to substitute into our expression. So we get 4 minus, and 2 sine theta squared is 2 times 2 is 4, and sine times the sine is sine squared theta. We then factor out our common factor, our GCF of 4, leaving behind 1 minus sine squared theta. So then on this piece right here, we're going to use the Pythagorean identity. And 1 minus sine squared theta is going to be equal to cosine squared theta. So then, putting all of that together, we get 4 times cosine squared theta. The square root of 4 is 2, and the square root of cosine squared is cosine theta. So then, that would simplify down to cosine theta. All right, so the next thing we want to look at involves our sum or difference identities, which we haven't used yet, and we're going to use them to find the exact value of 5 pi over 12. So if we were to look at our unit circle, the first thing we would notice is that 5 pi over 12 is not on our unit circle. So we grab our unit circle, and in fact, there are no pi over 12s on our unit circle. So if we're ever asked to find the exact value of something, we have to get it in terms of radicals, not just a calculator approximation. So if you just punch 5 pi over 12 into your calculator, it'll give you a decimal approximation, but then that will get marked wrong because it is not the exact value. So we're going to need our sum and our difference identities. So if we look at our identity sheet, we've talked about the Pythagorean identities. We haven't done double angle yet. That'll be a little bit later. But we do want to talk about our sum and our difference identities. I'm going to grab these because we're going to use them in a bit. So let's get back to our problem. So our goal is to find two angles that add or subtract to give 5 pi over 12, because that's our goal, right? We want to find that exact value. So to do this, let's write technically, let's rewrite some common angles with a denominator of 12. So let's start with our common angles that we have on the unit circle. So when I say common angles, that's what I really mean, is ones that are on the unit circle. So we have pi over 6, and then we go to pi over 4, pi over 3, and pi over 2. I mean, we could keep going, but it turns out these are going to be the ones that we're going to need. So if I rewrite these as a denominator of 12, I would build my first fraction, so pi over 6, by multiplying the top and the bottom by 2. So that's 2 pi over 12. The second fraction, to get 12, would need a 3, so that's 3 pi over 12. This fraction, it would be the top and the bottom by 4, so I get 4 pi over 12. And lastly, pi over 2, I'd multiply the numerator and denominator by 6, so I get 6 pi over 12. So remember, our goal is to find two angles that when we add them or subtract them, we get 5 pi over 12. Well, that's going to be these guys right here, because 2 pi over 12 plus 3 pi over 12 gives us 5 pi over 12. So that is then that pi over 6 plus pi over 4 is equal to 5 pi over 12. So now we can use one of our sum or difference identities. So our goal is we want to find the cosine of 5 pi over 12. So we really want to use this identity right here. So we have that the cosine of 5 pi over 12, or that the cosine of x plus y is equal to the cosine of x times the cosine of y minus the sine of x times the sine of y. So that's the cosine of x plus y is equal to cosine x sine x, y, and y. So in our case, we want the cosine of 5 pi over 12, which we just found was the same as pi over 6 plus pi over 4. So pi over 6 plus pi over 4. So then that means we're going to substitute all of that in. So we get the cosine of pi over 6 and the cosine pi over 4 minus the sine of pi over 6 minus the sine of pi over 4. So we have pi over 6, and our pi over 4s. So since we used only values that we knew were on the unit circle, we can now simplify this using our unit circle. So the cosine of pi over 6, so we go to pi over 6 and cosine is going to be x, and the sine of pi over 6 is going to be 1/2. And for pi over 4, we're going to have cosine is root 2 over 2 and sine is root 2 over 2. So the cosine of pi over 6, as we just said, is going to be root 3 over 2. So we're going to replace it with what it's equal to, root 3 over 2, times the cosine of pi over 4, which we said was root 2 over 2, minus the sine of pi over 6 is 1/2, times the sine of pi over 4 is root 2 over 2. So now, simplifying, the cosine of 5 pi over 12 is equal to square root of 3 times the square root of 2 is the square root of 6 over 4 minus 1 times the square root of 2 is the square root of 2. All over 2 times 2 is 4. So it's the square root of 6 minus the square root of 2 all over 4. We can use our graphing device to check that indeed we did get the correct answer. So if I go cosine of 5 pi over 12 and hit enter, I get this value. I can also check, is the square root of 6 minus the square root of 2 all over 4 the same thing? And they do have the same decimal approximation. So indeed, the cosine of 5 pi over 12, the exact answer is the square root of 6 minus the square root of 2 all over 4. So we can check to make sure our solution is correct. All right. So for our next example, we're asked to write the cosine of 25 degrees times the cosine of 20 degrees minus the sine of 25 degrees times the sine of 20 degrees as a trigonometric function of a single angle and then evaluate. So what we're actually doing here is the opposite or the reverse of what we just did. So if we go look at our identity sheet, we've got something that looks like this. We have cosine, cosine minus sine, sine. So if we look at our identities, we need something in here that goes cosine, cosine minus sine, sine. So sine, cosine, cosine, cosine plus sine, sine. So that's not right. Sine, cosine, that doesn't work. Finally, we get here cosine, cosine minus sine, sine. So we see in our sum identities, we identify that this is the cosine of x plus y. So we identify what our pieces are, and we see then that our x is going to be 25 and that our y is going to be 20. So we plug them into this side, and so this is all going to be equivalent to the cosine of 25 degrees plus 20 degrees. So that's the cosine of 45 degrees. And if we look at our unit circle, the cosine of 45 degrees is root 2 over 2. So that would be our solution to that equation. All right, so the next you try is for you guys. I want you to do exactly the same thing, with one exception. Just rewrite it as a single trigonometric function, and we are going to get rid of the and evaluate. So just write it as a trigonometric function of a single angle. All right, so we identify our trigonometric identity that we want to use is the tangent of x plus y is the same as tan x plus tan y divided by 1 minus tan x tan y. So in our case, it looks like x is going to be 0.25 and our y is going to be 0.75. So then if we put all of that into this, it gives us then, we have the tangent of 0.25 plus 0.75, which then 0.25 and 0.75 add to give us 1. So that expression would be equal to the tangent of 1.